The lecture today is about machine learning, right? But it will not be about coding. We will talk about the underlying framework of machine learning in mathematical foundation, especially when you're considering parameters together with the model and the tasks that the machine has to learn. How can we frame those in terms of mathematical construct, and how can we use mathematical techniques to solve the mathematical construct and find a solution that would help us addressing the problems. Let's take a look. Okay, when we talk about deep learning in our course here, it is a specialized application of machine learning, right? So in order to understand deep learning very well, we need to also look at the broader concept, the broader topics of machine learning. We can consider deep learning as the part of the larger box here, which is the machine learning, which is also another part of artificial intelligence. Okay, now let's formalize the notion of deep learning. So Mitchell in 1997 has defined deep learning as a computer program that is said to learn experience E, right? Learn experience E with respect for the task that it has to perform, the task T. And this task would have the performance measure P, right? Certain performance measure. If it performs the task in T and measure by P, and this will improve with experience E. So it means that with more experience, we can create a program that learn from experience how to perform the task and achieve the performance measure P. Okay, so this is like the formal notation. Now let's take a look at each of the components inside these elements. The first one is the task. Now, when we talk about classification tasks, right, that mostly we encounter that in the deep learning model when we want to classify like different images, right, or if we want to identify whether part of the image would belong to a certain class or not. In this task, right, the program has to do what? It has to ask a specific question on which category of the K category that the input must belong to. Like in the case of image classification of C410, there are 10 classes, right? Like there are like frog, I don't remember, airplane, truck, and cars, and others. So the task here would be to identify, to classify which of the K should input belong to. So when solving this task, the learning need to work like the following mathematical formula, that it has to map from Rn, from certain space, right, with the dimension n, mapping it to the dimension of 1, choice of 1 to k, selecting one of these out. And when we have something like y equal fx like this, we would have the model f that we have here, that assign input, right, vector x as input, and then classify it into one of the category, maybe the numerical code y. This is the task for classification. Now let's take a look at different tasks in machine learning, like in regression. In regression, the computer program has to again receive certain input and predict the numerical values, right? Predict it so that we can represent it as mapping between Rn to R, right, to just one value. So in a way, regression is quite similar to classification, right? The difference would be that the format of the output is different. from the class to the value. Now, how about this one? Clustering. Clustering is also another task. So we can think of clustering again as a program, a certain program that what would it work? It would divide the data into groups. Right? So that's the basic functionality. To solve the division of data into groups, the learning has to trying to map between Rn to again to the labels 1 to k, but now 1 to k we would not know the labels beforehand. So that's the context of clustering. Right, so that means the goal would be to divide the data into groups based on certain features, certain patterns in the data. For example, you can divide the data into the RFM, recency, frequency, monetary, and then perform customer segmentation to understand the behavior of the customer. Right, this is another task. Okay, let's take a look at a more complicated machine learning. Now, if you imagine, right, you can write the thing that you saw that use AI, use machine learning as this type of task. Try to think of it. What are the experience? What is the task that it perform? What is the measurement of the output? What are the input and output? Right, and then you get the constructs of the techniques. For example, this one, transcription. Transcription is a task that we often let the system learn how to change from speech into textual data. Okay, so in this type of task, machine learning has to learn the unstructured representation of certain data. It can be video, it can be audio, it can be image, and then trying to get the caption, right? So it can be a lot of things, a lot of different types of unstructured data. And then it has to transcribe the information into textual form. So this is the transcription. Okay, so how it works, like if you want to train a model to perform speech recognition, first you need to have the corpus, the recorded voice, by recording a lot of speech into the database, and the utterance would need to be varieties. It needs to have different types of context depending on the task you are trying to do. Back then, when I teach, if you want to do the system that recognize the speech like 0 to 9, right, the code like 0192, something like that, you need to have a context that the speech that recorded like that have the variation of the speech recorded from the actual humans. Once you have that, you also need to annotate the data manually, right, so that the data are labeled according to the pattern. And then you can input that to the algorithm, right, to do the speech to text STT algorithm, like using the LSTM RNN to do speech recognition, or using back then using the CRF HMM, the hidden Markov model, to perform speech recognition, remember the pattern. Okay. So from the input voice, these need to be paired with the right one and the wrong one, and then let the system learn, right? So that it can learn to change from the speech into the text. So this is a transcription task, right? The context can be different for the transcription task. For example, if the aim of the study is to map between image and then let it generate caption of data, then you can imagine that we need to create the data that includes both image and the caption, right? And then perform the similar procedure, right? We have one question coming in. Does without labels mean performing unsupervised learning? Yes, correct, right? For the clustering, without label, right? Unsupervised clustering, unsupervised segmentation. Okay, but there are authors. Actually, I cannot really cover all of the machine learning, different types of machine learning in this class. For example, Just think about the news that you may have heard. There were the news about we have AI writing code. How can it write a code? Then it means that the machine learning algorithm has to learn the pattern of dependency in the code. And it has to learn the context, right? The larger context of the code. The model that is usually used for that is the recurrent neural network, which we will learn later on, right? To do that type of task, do the text generation. Right? But well, let's formalize it in a general way here first. So let's take a look at another task here. Machine translation. Right? What is machine translation? A machine translation is again a computer program that input can be sequence of symbol in some languages, and it has to convert this into another sequence of symbols in another languages. So it has to convert from one to another, right? Back then, doing machine translations means that you need to use the full knowledge of natural language processing. Nowadays, approach has become more of data oriented. That is, given that you have similar utterance, right, comparable utterance, then you can let the system learn by itself on how to translate from one to another, just like that. So it means that back then, if we want to perform machine learning, machine translation using normal ML, we need to, from the source text, we need to analyze the source text into a certain detail, and then map from this detail into another layer of detail, that is suitable for generating the text in any languages, right? Sometimes they call this like, I don't remember the name, something like universal languages notation, something like that. I don't remember. But nowadays, instead of having that form and then find the kind of rule to generate the text into different language, which require the system to have detailed knowledge or detailed rules on how to analyze and synthesize both languages. These are difficult because in order to do so, you need to have experts, right? Natural language processing experts in almost all the languages, which are difficult to find actually. That's what I have been experiencing in the past 10 years working in the speech and language fields. Right now, I would say that Thai people, right now we have a lot more machine learning scientists that work on natural language processing study than having the language scientists that apply machine learning approach. You see the difference, right? For the field in language to advance, to have like more specific knowledge, they have to study like what are the effect of grammars, what are the particular types of utterance, what would happen, how to what are the difference between a different style of writing, and then how often that they are used. So those are kind of things which are actually important. When I study, when I work as a postdoc, these fields in English are huge. Right? The people studies on linguistic phonetics, phonology. In Thailand, these two are very small, but the larger field is machine learning scientists that try to solve the problem in language using ML. But the problem is that doing the machine learning, use deep learning particularly, doesn't really advance the knowledge of language. Right? So the thing that I'm talking about here, whether it's machine translation, transcription, clustering, these are deep learning are suitable. Machine learning are suitable for creating applications, but the findings that it show would not be something that is. It would not be something that is. Wait, I need to take a break. I need to take a short stop here. I'll be back. All right. So let's see. There is there was a question: is the machine learning, is the machine translation practical nowadays? Yes, quite so. You can see that in the conversion. Well, I would say quite so for English, for the Romanized language that use the like English alphabet, like English, French, German. They use kind of similar, like European language and English. But for that, it's quite practical. For other languages, I would say up to a certain limitation of translation, it works. But just like speech to text, right now you can talk to your mobile phone, but it will be up to a certain variation, right? If you kind of wear out of the patterns, then it wouldn't work, right? So, and the next question is, in this picture, what are the differences between transfer and direct translation? All right. When you take a look at this picture, right, we have the source text. Direct translation means that the text is translated at the lowest level, like mapping word by word, and then translate that into the target. To do the transfer, machine learning at the transfer level, it means that the source text has to be analyzed into a certain level that can be transferred into another language. Ideally, it would be like analyzed until it reached the interlingual level. That means whatever language it has, whatever language the target would be, it can be generated from the interlingual, which is like an ideal, right? It's not really practical in terms of this. Right now, we know that mapping from one to another is quite practical, but researchers are still struggling in order to find a way to generalize the weighted learn from machine learning for it to be applicable to multiple tasks, to create a more generalized version of the machine translation. Another question is, could you please give one example kind of machine translation, and how can we measure accuracy on the machine translation? We develop it later on. For this, I cannot actually specifically say what types of metrics that is used. I would rather refer to looking at the research. But to guess it, I would say that they would measure the performance in multiple levels. In the lowest level, this would be the performance of like the word consistency, right? At the higher level, like at this level, analyzing it numerically might be a little bit difficult. So if I were the researcher, I would perform something like perceptual evaluation that asks human to judge the to identify and read. Well, I would do something like A/B testing. Right? We have version A. These are the text that it has to be like that, like the actual translation, and we have B, which is the translated version by the machine, and then we can randomize and then test whether the one that have from the machine comparing to the one from the original translation, whether they are the same. But we probably can evaluate at the transfer level. But because, well, I would say that I'm not really the machine translation researcher, particularly to the field, so I'm not really sure on the performance metrics. I would suggest that you can find those out by searching on the literature, on the related literatures. For me, if you ask me what are the perceptual evaluation or the metrics on speech synthesis, then I can answer you for that. Never mind, right? But the tasks are quite the same. That for speech synthesis as well. So it works like this as well. Like you have the text and you try to generate the speech, the speech data. It has to go to something that is similar to this one as well. That is, you can, if we perform like direct translation, that can be done by just mapping that text has this word and then concatenate it together with another one, right? But when we perform something like machine learning or the deep learning of the text to speech data, We are trying to create a system that match from the text sequence to the speech acoustic data, and then let the system able to generate the speech data once it has the text input. Right? So again, it falls to the similar picture that we have here. Let's see. So these are the tasks. Now let's look at a different variety of tasks. This is a task that often find in business: anomaly detection. The task of anomaly detection is to identify the event, is to sift through the events and then alert when there are certain uncertainty occur. So this type of model can be used to detect or predict something like fraud, and then once detection occur, human can then inspect and then determine what happened at that point. Okay, you may have seen some of these. I have not really seen beside the paper. We can use machine learning to perform synthesis and sampling of the data. Like the task would be that ML has to generate new examples that are similar to those of the training dataset. For example, one of my students work on a thesis of generating speech data from the movement of articulators. So for him, he has to train a machine learning model to receive the articulators, the tongue and lips and jaw locations, and then once the system receives that, it has to generate speech sound. All right, so that's the thing that it has to do. So that is the synthesis work. Like you may have heard of the deepfake, that you can actually superimpose the face of anyone onto the sequence of video, thus generating a fake video which really realistic version of that person. Right? So this type of thing can happen and exist. That has never been able to exist before by manipulating these things. It has occurred in a lot of applications, not just in something like deepfake. We can have a system that you have an image, and then from the image, the system have to synthesize the explanation of the image. That is also the case as well. Okay, so the task for synthesis and sampling is to generate the new data. That means the system or the model has to learn these data as output, or a way to modify these data as output. And what should be the input? It can be the preceding frame, right? For sure, it can be the preceding frame as input. It can be the image of the thing that you want to merge with or you want to synthesize. And using both would allow them to create a task in a synthesis manner. This is not new. Not just after we saw that there is deepfake or whatsoever. Actually, there are trends in machine learning that when it progresses to a certain point, people or researchers in the field would try to create a synthesis system that would kind of remember the patterns and then generate the data. For example, in about a year of 1990 to 2000, my field, speech recognition, speech synthesis and recognition, to perform speech synthesis effectively, one has to concatenate, right? Take a chunk of speech and then concatenate them with another one, right? And then trying to find a way to smooth them together, right? That's the way that has been done to do speech synthesis back then in 1990 to 2000. After 2000, there is a proposal that, okay, you can train the model to remember patterns. One can use a hidden Markov model to analyze the pattern and classify data. But the other application is to train it so that it remember the pattern and then use that model to generate the data out. And that is actually the synthesis and sampling process. Right? So the task in this manner is to generate the new data set. Okay, so these are lists of examples of tasks in machine learning. You may have thought of the other thing, like there can be something like tracking. You can do the tracking as well. You can perform something like the time domain forecast. What else in machine learning? You can do the planning, right? Generate the plan rather than generating the data. So there are multiple ways to define the task. These are examples, obvious one. Different type of tasks would have different types of performance measures. As I said, to know it thoroughly, I would suggest that if you want to work on that field, I would suggest you performing literature review, just like in your thesis. Once you accumulate multiple works on that field, you will see a proper numerical metrics of that the fields use. I don't want to just impose or suggest that this should be the things. So for example, precision recall accuracy might not have been seen at all in the work about classification because you may see the number like AUC, AIC, which are different types of measure that, but it can be used as well to measure the classification model. Nevertheless, let's take a look at a few of them as examples. For further your knowledge, I would suggest read a lot, right? Read the paper in the fields that you are interested in. For this class, we will have the term paper presentations at the end of the semester. You need to select one of the paper that you like and then present the deep learning technique contained in that work, particularly about something like the architecture of the model, why does it work, and then explain it mathematically on the rationale that the author offered. Think about it as literature review of one paper about deep learning, right? Okay, so for classification, there are multiple metrics that can be used. First three, actually the one that is obvious is accuracy, that you can obviously to determine the performance of the model by considering accuracy. Well, when you compare the actual data with the predicted data, you can divide the chunk of prediction into 4 parts. The first part is the true positive part. The true positive is the part or the group of data that your model predict as positive, right? But the actual data is actually positive. So this group of data would be the true positive set. False positive set means that the model predict as positive or yes, and the actual data is actually no, right? For example, the model may detect that this person might have, say, cancer, but in fact this person doesn't have it, right? A lot of medical tests has a lot of false positive because it is cost less when you detect things earlier than detect things later for the medical reason, okay? But different business would have different perspective on this. I was once talk with the lead, what should I say, I would say one of the management team in big company in Thailand, and they're really concerned about false positive because false positive means that they kind of offer things to customer without really need to, and that's not good, right? Why reducing your own profit without really need to do that? Comparing to false negative, which means not offering why the customer might want. This can be recovered by doing other things like offer it again or doing the offer with a different approach. So it depends on the task, the performance that matter to that. The true negative are those set that the model predict as negative, as false, and it is actually negative. Right? Sometimes this doesn't mean anything. Sometimes this class means something, like you try to classify between class A and class B. For example, you want to classify between the text is positive or negative or neutral, right? There can be 3 classes as well. Okay, the metrics that can be used, the first one is the accuracy. Accuracy is the combined of the true positive and negative, the diagonal here, divided by total. Okay, accuracy is a little bit problematic if the class is a bit skewed. Okay, so there are other measurement like precision. Precision measure this true positive comparing to the whole predict yes things. Recall comparing the true positive that model can detect with the whole set of true set. Okay, this can be better explained on the right hand side. On this right hand side, when we create a model and perform prediction, you can have the precision coming from the left hemisphere here, on the left part of the circle divided by the whole circle. This is precision. The circle itself is the selected elements from the model. Recall would be the left part of the circle and the left part of the square, right? And we have like the ratio between the detection of the relevant elements. These precision and recalls are a little bit of trade-off. So why is that? Recall has another name. I should point out. Right. Recall has another name, which is the true positive rate. Why? The false positive rate is actually 1 minus precision. Don't mind my writing. It's a bit hard. Oh, why do I have to write like that, right? Sorry, let's erase it. Shouldn't be there. Right, this is 1 minus precision. Alright, so here you can see, and the green line here indicate different model behavior when you select the data at different threshold. Usually, when you perform machine learning model, you will end up with the result that look like this. Say we have something like ID on this column, and the probability of yes in this column. Okay, so if we rank it from a large value to a small value, and then we perform selection, like from at the top, like say this level, it might result in a certain point in the curve. In another level, it might result in another point in the curve. Okay, so I mean, when you set the threshold of the probability to be different, it is possible that you will have multiple points in this curve. And when you draw a line, of the curve together, you get this green curve. This is called the ROC curve. The receiver, I don't like this. Sorry, I don't like this icon following. I turn it off. Annotation. I think it's a feature somehow that I accidentally turned it on, but it's quite annoying actually. Receiver operating characteristics, or the ROC. This is U. It's actually the AUC, area under the curve. Right? So once you get that, you can draw the AUC line, ROC line. This ROC line would show you the behavior of the classification model, particularly the binary classification model, to identify the tasks that you want. It has the value ranging from not more than 1, because the square here is 1. The worst value is about 0.5, but it can be less than 0.5 to some sheer luck. But well, 0.5 means random. It means that you kind of randomly selecting the class. The good curve would go up and then create a lot of area under this curve. Area under the curve can be used to determine the quality of the model. That is usually like the rule of thumb. That is, if the AUC is more than 0.6, this is like acceptable, but not good. more than 0.7, this is good level. Oh, good. When something following the drawing is confusing. When it is more than 0.8, then this is the very good or excellent. More than 0.9, dot. Just be sure that it's not wrong. Because it's hard, or it can happen if the problem is easy, right? So this is the performance of the classification model. You can see that there are quite a number of things to consider here. I have not covered all of the performance measurement for the classification. This is just one of the possible for the binaries classifications. Okay, let's move on to the next. Oh, we got the questions or the comment coming in here. Let's see. Accuracy can be defined in terms of probability, like success case divided by total case. It actually is. It's a success case, or I would say successfully predict case. Successfully prediction case. So that's the accuracy. Not in terms, well, it is a bit of probability because the value will be less than 100%. Because we have like the total number, we cannot predict more than total anyway. Yeah. So it's more like up to 100% the fraction, right? Okay, move on. Right. For then it can plot in activation function. I think you might have been misunderstood a bit here. Plot in activation function. Say, let's put it this way. When we perform classification or when we perform a task like this, we usually have the training data that looks like this one. And you have this like X and Y, the label. The label can be like maybe 0 and 1 and so on. Then we use the X here to train a model, and then we can have the prediction. The prediction would have the value quite similar if the model is correct to the Y here. Think about it as Y hat, the prediction. And then our task now would be comparison between these two together to evaluate and then come up with the measurement here. In scikit-learn, there's a function like the classification report. In sklearn, don't know what happened. Yeah. Or for the AUC, there is, I think, ROC_AUC in the scikit-learn, right, that allow you to assess the quality of the model. So it's not yet related to deep learning. I would think about this as a more of the larger context of machine learning. Right? Like if you want to classify the churn, whether plasma will churn or not, then it would be this one. Okay, the question coming, does it mean if ROC is almost linear, the model is good? Is it because some model will give the same level of accuracy when it does? No, ROC is not like that, right? When you look at this, when you look at this curve, this is true positive rate. This is a false positive rate, right? Or it is the 1 minus precision. As you may know, when we have a model and then we rank the model based on the probability, the upper one, maybe 0.95, 0.945, so on, would have high probability, right? Then we can say cut at the first 10%. Okay, if this model is good, right? If this model is good, it would be it would have high precision. High precision means low recall, right? And it should cover a lot of data, and that means it would have something like cover it up to this point, the true positive rate value. Okay, now if say we want more true positive rate, we would lower this line to say this point. Once we lower that to this point, so we have to consider the whole thing from the above down here. So it is quite logical to assume that the precision would drop, and when the precision drop, it means that the point here would go to the right a bit because the false positive rate will be higher. And then you can also make cover more data, and that means if the model is good, you should kind of cover more true positive rate while having a bit increase in false positive rate. Now if we lower it a bit, and then we'll get something like this one, and then when we draw a line, we get the ROC curve. This is good model, right? This is good model. What does it mean by having bad model? Right? By having bad model, you can consider this vertical line. In this vertical line, when we are trying to lower the threshold, the proportion of false positive rate would increase at the similar ratio as the proportion of true positive rate, which means that the model doesn't help. It means that it is similar to random, right? So for the AUC, the diagonal line is actually the worst case scenario. This is like if the ROC line fall into the diagonal line, it means that your model is similar to just random, right? Think about it as like the just random sampling of the data, and you get the same thing, right? So having this going up, the steeper the better. The best model would have AUC like reaching the value of 1, but usually in practice it would be something like 0.8 something, right? When the AUC is more than 0.9, it means that there are certain clues in the model that give away the prediction. It's like you might have been included the output as part of the input, and that's not a good idea. All right. Okay. Any more question about the classification performance? If you are still not sure, read about ROC, right? And then if you are still not sure, you can post that into the group. So we need to get linear result. Your model is program a system that process input of sample data and get output result. No, classification means that if I want to answer your question directly, no, it's not linear. It should be sigmoid, or it should be softmax in terms of activation layer, because what we want would be to identify whether this is like 0 or 1, or whether this is like 0 or 1 or 2 or 3, and these are all class. So when we get the value as sigmoid, this would determine whether it should belong to this class 0 or 1 or not, right? When we have like multiple node and then performing softmax, it means that we are trying to find the maximum probability of all this, right? So it's not linear, okay, in terms of activation function of the final layers, right? But well, that's beside the point, right? The point here is in terms of the performance measurement. Okay, let's take a look at this, right? That's for the task of classification. For the task of regression, right? Regression, there are multiple ways to measure the performance of regression model. One of that is the R-square. Right? R-square would measure the variation that occur based on the model comparing to the mean. So R-square would measure the, what should I call it? I would say it would measure the variation that the model can explain. That's one way to put it, right? So it means that if the model can explain it quite well, you would have the difference between the point and the model really small comparing to having the point comparing to the mean. Okay, so this means this should have high R square because the model can reduce the errors that is occur from the remaining of the prediction part comparing to having just the mean. So when you compare R square, you think you can see the similarity in the concept between R square and the AUC, right? Because both try to compare with random. Right? So this also try to compare with random, the mean one, indicating the random part. Another way to measure the performance of regression is to measure the difference between value directly, like the mean absolute error, MAE. This comes from the absolute of difference between the prediction and the actual, right? So that's the MAE. And these are for regression. For the performance, we need to also considering dividing the data into trend set and the test set. Right? But when you have trend set, we can perform tuning using cross-validation with the trend set. Once you get the model, then you can use the model to perform tests with the test set. With that, we will have the best version of the model so far from the test set, and then use it to validate the model with the test set. Okay, so this is the method that allows us to evaluate the model. Okay, and this is actually not the performance. Well, this is the experience. I forgot to share it because when you give the data to the model, the data itself will become the experience that the model has to learn from. It has to learn from the training set to capture the patterns and perform prediction with the test set. Okay, the way to perform prediction and evaluation is one of the ways to, well, this is called hold out technique, right? The hold out technique would hold part of the data that used for training and then use another part of data for testing. Another method is called cross validation, right? Or we can use them both, like hold out can be used to separate the data into training set and test set. And then in the training set, we can train and tune the model. To tune the model, we need a way that you can test multiple parameters and test whether the model is overfitted or not. And that can be done using cross-validation. How does it work? In cross-validation, you need to split the data into multiple fold, right? Like this, this would be 5-fold. And for each fold, you can use one of the fold to be the test set, and the remaining 4 to be the trend set. And then we can do this 5 times and combine the performance together. Well, this is cross-validation, right? Although doing cross-validation is good, but in many applications this is quite resource intensive. You might need to kind of sampling the data to be smaller set in order to perform cross-validation, because if the data is too large, like say 10 million rows, and you need a very computationally intensive computer to work on that. Right. Let's take a look at some of the example of the problem and see the tasks. Let's see what is the task, what is the performance, what is the experience that need to be given in order to perform machine learning in this respect. Let's start with the simple linear regression. In linear regression, the idea of linear regression is to solve regression problem. That is, you have the data set and then you want to explain y given x. You want to explain the output with respect to the part of the input. So the idea here is to build a system that take in vector x as input and predict the scalar value y, right? So that means the output would be linear function of input, like your friend said that. That's for linear regression. Okay. So we will have this y hat to be the value of our model that predict for y, and we can write it mathematically as y hat. This would equal w multiplied with x. Okay, this is the dot product between w and x actually, although it's right as the transpose, but you know that vector multiplication of the say column vector and the row vector would result in the dot product between the two. Okay, so and w here is the vector of parameters. We multiply the vector of parameters with x. Now let's decompose it into task, performance, and experience that need to be given. First, the task. The task for this would be to predict y from x. Right? Predict y from x. Right? Very simple, straightforward. The performance measure. Now there are multiple ways to do that. Let's say one of the ways to measure the error, right? The square error, because we don't want sign. It can be the square error and then find the mean. This is the mean square error. This can be the performance of the system. But it can be other as well. It can be the mean absolute error, the one that we talked about before. It can be R square. That is also applicable here. I just want to put in examples here. Okay, because this mean square errors has a certain relationship to the way that we derive or learn the experience from the model. Let's see. This is the way that we have already covered in the linear algebra review. That is, from the mean square error of the training dataset, we can take derivative of the mean square error with respect to w, and then set it to 0 in order to be satisfied with the least square criterion. Least square criterion means that we can find like the bottom point of the curve by finding the point that have the gradient equals 0. So take derivative and then set it to 0. Then we can solve the equation. So by expanding this will be y and square, y train y hat minus y square, and take the derivative by w, and this would be x, w, and y, and then so we can remove 1 over m out, and then we will have the first and the second. This is transpose and its actual value to denote the multiplication. And expanding the terms by multiplying, we have w transpose and x, and then x, these two terms. There are a little bit of shuffling in the location of the terms due to the multiplication of matrix. And 2 of wx and wtx, right? So this would be where okay, wtxy, yeah, x and y, and this is y, x, and w, y, x, w, 2 of them, right? And y, right, y square, and take the derivative of the inside, and you can see that some of the terms do not have relationship with w at all, like y square here. So this has to be disregarded out, and the terms that contain w would be reduced by 1 w, which is this one, and this has like 2 w, like w square. So moving 1 out, we got this. And for this, we remove 1 w out, so we have 2xy, and then rearrange it. We have w equal the pseudo-inverse solution that we worked on before. Right? So you can see that it ends up at the same criterion here. But these are the experience. The experience part is like the way that you can map from the data from the model to the weight, right? To the part that the system has to learn, and this is experiencing of the model. Okay, so that what does it mean? It means that for linear regression, it has to learn the weight, right? Learning the weight of this line, So that this weight would be the lowest point in the mean square error curve. Okay, we have one question coming in. Can you explain again how to derive from line 4 to line 5? I'm not sure how to derive. Okay, line 4 to line 5. 1, 2, 3, 4. This line. No, I would suppose that this into this, right? The derivative. 3 running out. This is like a vector calculus, like take derivative of vector. So in order to make you, okay, I will answer the easier one that Simon asked first. Where does it go for 1 over m? Is the constant, scalar constant. You can just throw it out in because the other side is 0. So you can just cancel it out. Whatever, it doesn't matter. Okay. And for Nathanon and Phumpop, these two lines, these are vector calculus. So think about this as x squared and w squared. When you take derivative of w, you would pull the 2 down, right? And you have w remaining. Or not that line, the upper one. How come this become this line? Okay. You can see that this is just multiplication. I would say, do you remember the term like, oh, what does it mean by this one, right? This is a norm, right? This is something like the norm square, right? The norm square. So what is the norm? The norm of the vector is the square root of element in each dimension, right? Square root of the element in each dimension square, and then you sum them together, you get like the size of the vector, right? But we can represent the norm as the multiplication of the two vectors. For example, if I were to find x norm here, which is actually let's say x1 square plus x2 square plus dot 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 plus xn square, right? So it's actually this one, the sum of the product of the value itself. So how can I get the this can be formalized into something that is similar to this one, which is x as a vector transpose and then multiply by x, because when you have like x as a vector multiplied by x is actually the same one as the above, right? This means square root of x1 square plus x2 square plus x3 square dot dot to xn square. This is called the norm. Yeah, the L2 norm. And having squared it in the above means that you kind of disregard of the square root. Okay, so from square here, this means square error, right? Like you get the value and then difference and then you square it, and then instead of, because this would be a vector and a vector, then you can rewrite it as the transpose multiplied by its own value, and then you can just multiply them together. Right? Think about it. I would ask you to think about analogy like a minus b and square. You know that this would become a square plus 2ab. Nah, it's not plus, it's minus. This will become a square minus 2ab plus b square, right? Absolute square. Then we have something that is similar, that from the above here we have something like a square. It's actually xw, but it's still xw square, and then minus 2ab, right? Minus 2 and then a xw and b and y, right? And b square, y and y. That's why we have that something that looks like this line. right? And then expand the terms. Take a derivative by W and change side. Change side because we want W. We would change side. Put this one to the right hand side, and put this into division. No, it's actually if you want to make division in this equation, you need to calculate the inverse. Right? Calculate the inverse, and then we get this as the inverse. So this is the same formula as in pseudo inverse. All right, let's move on. Okay, so for the regression, we have the way that we can learn weight, which have the lowest value of the mean square error. However, when we have a regression model that is too complicated, like this is the data, we have b plus wx, we got this line. If we have the model that is suitable at the certain level, like this quadratic equation that explain the variation of the data, quite appropriate capacity, quite appropriate complexion, then complexity, then we have the appropriate, the suitable level. Having higher level of model like 9 order here would generate something like overfitting of the data, right? And this is quite serious in the machine learning, because once you have a model that is overfitted, the model would just remember the patterns of the data and cannot be generalized to apply to all the dataset, and that is useless actually. Okay, so this is a notion of overfitting in classification. Now you may have the data divided into two parts. Well, appropriate fitting would be something like this one. That is, you can sacrifice a bit, but you can have the nice separation between the two. But if you have a perfect model to the dataset and very high learning accuracy for the training set, like this one, you can see that the region that you get, the red line, is not suitable to use for the new dataset, because it's quite specific to these two, which can be errors. Right? So this is overfitting in classification. Okay, if we plot the error curve comparing by time based on the capacity, this capacity can be iterations that you train the model. It can be the complexity of the model, right? And when we increase the complexity or capacity of the model, and the error will decrease at the beginning, right? The blue line indicates training error, and the green line, the generalization error or the validation error, right? It would reduce to a certain point, and this certain point, after passing through this certain point, the right hand side here is overfitting zone. That is, you have the error increase, the generalization error increase, while the training error still decrease. You see that when we train the deep learning model, right, using Keras as a tool, this often happen when we use when we perform the task, because the model would be quite complex and our data might be too small, or maybe we might train it too many layers and then it will create the situation that the model is too complex. This is not limited to deep learning though. Right? If you work with something like gradient boost tree, random forest, you may encounter a situation that you put in too many trees, you put into the deep too deep of the model, and that create a kind of worse performance in terms of the generalization error or the testing error comparing to the simpler one. Right? I just encountered that today with one of my project, right? That I use gradient boost tree to do the job, and I set the team set the parameters to be quite complex. The problem with that is that initially we thought the number is good already, but once we reduce the complexity of the model, the result is actually even better, right? And that's come from tuning the model using cross validation, and that allows us to understand this. Okay, let's take a break, right? Let's take 10 minutes break, and we come back to no dinner. Oh no, it's no free lunch theorem, right? Not no free dinner, right? From Walpers. Okay, so these are quite fascinating theory that people thought of about the learning process in the machine. Think about it as the core of AI. If you want AI to be able to learn to do tasks, right, you need to think about these things. These are the things that we humans think all the time, and some of them has even been incorporated into our decision making. Right? To do it with computer, we need to find a way for the computer to learn this principle, right, without exactly program it to do so. Right? And then when you take a look at multiple papers, all of them were trying to do this in different tasks. All right, let's take a break. Right? We'll start again on 7:32. Right, let me charge this iPad a bit as well. Right, let's continue. So, according to the thing that we learned earlier, that if you get the model to be too complicated, right, the model can be overfit. Right? If the model is in this region, it will call to be that the model would be underfit. That could occur if the model is kind of have limited complexity. I cannot cover the explanation well, like in simple linear regression model. Okay, so I would say the researcher in the area, the scientists in the area, so they have this proposal that when you have data, right, with so let's look at it word by word, literally. The average overall possible data generating distribution, every classification algorithm has the same error rate when classifying previously unobserved point. This is called the no free lunch theorem. Right? So if you're trying to interpret this into the machine learning way, this would mean that the idea of machine learning is to seek the universal learning algorithm here, but it would be that we want to find is to understand the process and find the best algorithm based on specific data. So that means specific data set, one model may perform well, but when the data set change, maybe because of the nature of the data set, maybe because of the distribution of the data set, the model would be able to achieve to a certain level, right? So that is the meaning of every classification algorithm would have the same error rate when you have like a certain distribution of data. Okay, so it means that there is the limit. There's a limit in learning from the patterns of the data. Okay, so how do we deal with overfitting? How instead of trying to achieve the best learning from the data set, certain data set, what should we do? We need to incorporate other types of constraints into the model. One of which is to regularize the parameters. Regularization is the concept of that we trying to incorporate the terms into, for example, the objective function. Right, we're trying to modify the training criterion so that it includes the decay of weight. Right, it includes the usage of the parameters. So instead of having just MSE, we will have MSE together with the weight, right, the L2 norm with the weight. And we will have this rate lambda, which controls the strength of the regularization. If lambda is 0, we say that there is no preference. But if we have large value of lambda, it means that we prefer that the weight would be small. Okay, this is regularization, and it can help decreasing the overfitting of data. So with lambda approach 0, we have data at overfit level. When we increase the value of lambda, right, the model would be more appropriate. We would have like a more appropriate level of model. But if the lambda is too large, it means that the model would need to favor the weight rather than the error, which is unreasonable in machine learning, and we would have like underfitting case. Okay, so there are other ways as well. You can see this is one of the ways to include the regularization as part of the training model. There are other ways to include regularization to the model. Right? This different approach still called regularization. For example, we'll see later on in our deep learning course that you can regularize the neural network by doing dropout. Right? That means you randomly drop the node out of the network, pruning the node. Or you can perform regularization by transforming the input, right? So that your input would be transformed like rotate or zoom at different level. Right? So that can be done, right? That also generate types of noise into the data set, which would force your machine learning to take care of those noise. And this is part of regularization, so that the model would not be overfit to just a simple example. So just think about if I were to quiz you guys with random questions, that would be something like that. Okay, so that's the concept of regularization for machine learning. Now, different machine learning would have different other unlearned parameters. These are called the hyperparameters. Hyperparameters are the setting of the model. For example, in decision tree, you can set the depth of the tree, right? So that it can learn at different depths. In random forest, you can set the number of tree that you want it to learn. In linear regression or maybe logistic regression, you can set the regularization parameter, and that is actually the hyperparameters of the model. Right? The hyperparameters are the variables that the parameters that cannot be learned, cannot be adapted by the algorithm. For regression, like polynomial regression, the hyperparameter can be the degree of polynomial, the order of polynomial, right? And for the other example, we have lambda. That is also the hyperparameter that need to be set or need to be searched for that. One of the two of my students work on this thesis to try to find a way to optimize for the hyperparameters iteratively using something like evolutionary computing. But this are very active field, so you will see later on there are multiple proposals on how we should use different type of parameter tuning or the hyperparameter tuning to find the best set of parameters out of our data set. What is different between hyperparameter optimization and regular training? Okay, regular training would use something like this, like the loss function, in order to find the weight, right? So that's the regular training. Hyperparameter, for example, lambda here, cannot be trained, right? So because the objective function only reflects just w, if it also train lambda, it will be circular reasoning, and you cannot do that because if in that case, then the model would just say reduce lambda to 0, done, right? So it cannot, because in this case you want lambda to be certain constraint that you put into the model, and that cannot be trained, but it can be tuned, right? So if I were to answer your question there, I would say that okay, let me join the group again using this. Stop. I would say that for the normal model parameters, for the regular training, you use it together to train the parameters of the model. Sometimes we would call for neural network, this would be the weight. Sometimes it can be the structure of the model, right, together with the data. All right. For the hyperparameters, right, you need to do the tuning to tune the hyperparameter. How does it done? Then it means that, you need to build a model and evaluate, and repeat doing that with different combination of hyperparameters. Sorry for the shorthand. You need to have different combinations of the hyperparameters on each of the loop of evaluation. And this is usually done in something like grid search or the search, different type of search algorithm to search for the best parameters. Okay, let's see how it works. For example, if you have something like you have data set like this, we want to predict the quality, we want to predict the label here. We can build a random forest, and this building of the model for the model to build like this, you need to specify parameters like number of estimator, the maximum depth of the model, the maximum number of features to be used to build the model. These are hyperparameters. So you can optimize for the best parameters out. How to do that? Do for loop. Try them all, right? Do for loop and try them all, and then you get the best one, right? That's the naive way, but well, that is the most used way in machine learning field. Right? Once you get that set of parameters, then you can train model and then test the model. Right? So the step size of learning rate is also hyperparameters, isn't it? Yes, right. The learning rate is also hyperparameters. There are lots of hyperparameters related to deep learning. Too many, I would say. So that's why the newer version of the model, when they come up with something like auto AI, you don't have to think about this at all. They will do that for you. Right? This has become a certain time. It has become a popular idea, and people just throw it out. Doesn't work because many depends on the setting. These have settings, and it's not just the hyperparameter like this. That's for deep learning. There is also all the hyperparameters like the number of layers that you would use, the number of connection that you would like it to be. So there are a lot of like dependency in the architecture, not just in the hyperparameter that would dictate, or that would kind of indicate the way that the model would work. But yeah, for machine learning, one need to do hyperparameter tuning in order, and together with cross validation, in order to find the best parameters, the best hyperparameters to use. Okay, so to do that, the model, we need to have multiple instances of the model with different parameters combination. And then for each of these, it has to perform the cross validation. Like this, we have 0.9, 0.8, and 0.95. This is the best version. So we got this one as the best parameter out and use this to train the model with the whole data set. And then, so the whole train set. And then we can use it to test with the test set. All right. Yeah, doing cross-validation, right? Zooming in with one of the model, it would be like this one. Right? Split the data into a fold and then perform training with the white and then test with the blue and then got the error out and then or the accuracy or the metrics out and then average them to get the average performance measure. Right. Okay, so that is the hyperparameters. Okay, now let's take a look at the parameters learning. Right. What we can do in parameters learning, we can estimate the best parameters out of the whole thing as a point estimator. Point estimator means just estimate the point. So we have, if we have like this x1 to xm be the set of independent and identical data points. Say we have m data points, and from the m data point, what we want to estimate is the lambda m. Right? This lambda is the point estimator of this function. Say it's like the estimation, just aggregation function of the a number of points, and then you get one value out. This is point estimator. Say this might be the best parameters that we want, and this comes from the learning function. And if we take the learning function, we take a number of points in, then it will produce one point estimator out. Think of it in a simple way like this one. Now when we have this point estimator, right, we can define the bias of the estimator as the bias of the estimator is the expected value of the estimator, right, minus the actual value of the estimator. and then we will see whether the model has the bias. So this is like taking average of the model and then compare it to the actual value of the model. If there is a bias, then you will see like there would be deviation from the expected value. So expectation is over the data and the theta true theta is the underlying value that you want to know. So this is like the deviation from the underlying value. If the model is unbiased, then we would have the bias of theta equals 0, means that there is no deviation from the actual parameters and the expectation of the one that we got from the model. So in machine learning, it is actually a trade-off between the two, right? Between what? Just take a look at this equation. This is the mean square error. Mean square error is of this is the comparison between the parameters and the actual model parameters, right? Actual parameters, and square to denote, to discard the sign and find the expectation. This one can be breakdown. Right? This one can be breakdown into two parts. Right? The first part is the bias square, and the second part is the variance of theta. How does it break into these two? Is actually in statistics. If you remember the way when we calculate something like the expectation of moment or moment 2 of the random variables, or say think about variance, when we compute the variance, or you can get like the summation of the value square with the square of the value, something like that. So the breakdown of this would be something like those. So if we kind of move the expectation value inside, we would get this to be equal to the bias part square and the variance part square. So the whole thing here is just to communicate with you that because the model, you can see that the model, the machine learning model, rely on mean square errors, and the mean square error is also related to bias and variance of the parameters. So this plays an important role in dealing with variance and bias. Right? The model has to deal with variance, and the model needs to deal with bias in order to reduce the mean square error. Different types of model would deal with this differently. Okay, so overfitting can also be explained in forms of variance and bias as well. In this level, this is the optimal capacity of the model. It's a level that when the generalization error go down and it reach to a certain point, and then it becomes and it increase again. Right? This is a point that the bias would reduce further and further. Right? So you try to reduce bias further and further, and the model would try to capture a lot more variation, and until during the overfitting, it will capture just the variation, not the actual bias of the model, or the actual I would say main effects of the model, right? Because it will capture just the variance, and the overfitting occur because of the lack of bias capturing, and then the model would capture only the variation that occur in the data, and that's the explanation of overfitting. Okay, now let's see what different way to deal with variance and bias in terms of parameters learning. Let me check. Okay, now let's see. We have x as a set of m example, mx1 to xm, and we have this probability distribution of this as p data x that will generate this x out. And now this p data would reflect to a way that these x are generated. We also have this p model x given parameters. This is the probability distribution of the model that explain the data, okay, with certain parameter theta. In a simple terms, right? P model x would map X to certain probability of P data X. It would kind of map from the value of X to the probability of X belong to a certain output of the P data X of the actual data. Okay, so in the ML, in the maximum likelihood criterion, this is the way to define to find the best parameters. The name suggests that it was trying to find the value, the maximum of the likelihood, right? Try to estimate the parameter that are likely to happen. Okay, and in order to do that, the theta of the machine learning model of the maximum likelihood would need to come from the maximum argument of P model X given theta, right? It should be the theta that maximize the probability of the model, because let's think about it. If the model can predict high probability of the class, then it is a good model, right? Let's say if it can predict high probability of the class that it's supposed to, that is a good model. So it should pick the one that gives the maximum probability of the model, given probability of model that have X as input and the parameter theta. And this would be similar to if we decompose set X into a smaller sample, the multiplication of P, probability of the model, when we have multiple data set, and converting mathematically into the log pop, that would convert the multiplication into summation. And this would be maximum of from the maximum theta of the multiplication of the product. This will be converted to the sum of each index and the log of the probability of the data set. What is the P of X in the X in the model and parameter theta? Think about it as like, I think this would be a simpler one, like the number of spam message. Oh no, it should be the number of word. Can be something like the number of word, say Rolex, divided by number of spam message. Number of message with the word Rolex. Right. This is something like the likelihood that we will observe this word in this spam set. So if we talk about the model that will predict the spam, then this would express the P model of X of being spam given the parameter theta. Right. So think about this. This is called likelihood. Likelihood is the distribution of data that when we consider that it belongs to a certain class. All right. So the idea here is to find the best parameter theta that would maximize the likelihood, and that would be to maximize the expected likelihood of the log P of the log of the probability of that class, of the log likelihood. Okay, so how does this help us? This is actually the explanation of how the parameters come from. It comes from the evaluation of multiple value of theta, and then find the one that gives you the best expected likelihood, the maximum likelihood. So one of the way to interpret the MLE criterion that I just raised is to view it as is trying to minimize the dissimilarity between the distribution P data defined in training set and the model. So that can be explained by using the KL divergence that we talked about back in the review of the technique. That is, the divergence would be the P data given model, right? And the P data given models come from the data distribution minus the model distribution. So there will be the different distribution between the data and the distribution from the model. And the expected value, this denote the summarization of all cases. So all this, well, you wouldn't do this in the actual machine learning concept, but it has already been incorporated in a technique like decision tree. Right? So in decision tree, the KL divergence of decision tree is actually information gain. Well, if you take a look at the way that it works in information gain would compare the preceding the entropy of parent, so just like this data distribution, with the one that you use the model or the one that you use the parameters to divide, right? So that's the model. Then find the one that gives you the highest expected value, right? So that's the idea. A lot of machine learning algorithms already incorporate that technique, the KL divergence, the MLE criteria into the model to improve the model further by finding the one that best maximize the difference between the likelihood of the distribution, the difference between distribution of data and the one that the model can generate. Okay, so in that training, we need to minimize the expected value of the log P model, and this is actually the criterion of decision tree. Right, the criterion in the information gain. If you are wondering how does it work, I suggest read the manual on decision tree and try to find information about the keyword that I put here, entropy and information gain. And after you find it out, compare the equation that you got from the entropy and information gain to the one here. You will see the similarity between the idea that people thought of in terms of the maximum likelihood concepts. Okay, and when you see that is actually the best. I think it's actually the simplest version of MLE that you could find in decision tree. And then further, you can take a look at the other technique, like I would say. Well, the other one are not quite obvious as the MLE. So logistic regression, that the one that you actually work with right now is actually relying on the MLE as well. Right? So maybe you can try finding out, like comparing entropy and information gain decision tree to this MLE interpretation, and then again compare it to the logistic regression that you are working on. Right. So that's the MLE for the conditional log likelihood that we're trying to find the probability of y given a certain x. That mean we would have to find this argument max of theta, and this is the summation of the log likelihood of y occurring given we have x and theta, and this is actually the criteria that we see in a lot of machine learning model, because we are trying to predict the y given a certain x here and the model that we have. Okay, let's take a look at example here. Let's now think of linear regression as MLE. Right? We have already seen linear regression as the simple machine learning task. Now let's frame it into the MLE and then tease apart on how does it work on each of the component to be the MLE. So linear regression take input x, right? So the input x and then try to predict y. That's very simple. Right? It map the mapping the value is to minimize sum of square error, right? And then we get the relationship between x and y as linear equation. Now let's just think, instead of predicting only y, now think of the whole thing as to producing conditional distribution of py given x. Now what does that mean? it means that instead of thinking about it as minimizing the error here, we are think of it as the probability distribution. That there is a high likelihood here that for a certain x, it will predict certain y, right? That it will predict certain y for one value x. We have like y0 based on x0 here, right? There is a high chance that we get that, right? The other would be like errors that could occur. Now the goal of learning would be different. Right? The goal of learning would be to fit distribution py given x to all the value of y so that it would be compatible with x. Py given x here would be normal distribution because the one that we should be predicting should be the highest probability. So we would have like a bell shape normal distribution of y and sigma square, and then x would be the y hat and then x and w that we have. And here the distribution would be y minus y hat because we are predicting the y here, and this would be the distribution of py given x. Now the log likelihood of linear regression that we frame in a different way would be the summation, like from this py given x. Take the log and summation. Right? We would have it as this log of the distribution that we have py given x and the summation. And then once we have log, we can apply the log probability, that is the log of multiplication is actually the addition. Right? So we have log of multiplication 1 over 2 pi, log of 1 over sigma, and minus of the exponential, and the log would cancel each other and you get only exponent. Log of, yeah, is it the inverse process of MLE? No. Well, to say inverse process, this is a process of MLE, right? I would say, I think what you want to ask me that is that whether MLE is an inverse process to find parameters. If that's the case, then yes, it is. Yeah, it is. It is the MLE is actually the optimization criterion when you think of everything as likelihood, as probability. Right? So for example, instead of thinking of linear regression as minimizing some square error, we can think of it as the probability to get the right value, to predict at the correct value, and the remaining would be error, so that we can define the model prediction as the likelihood to get the right values. That's okay. Yeah. So what I'm getting at, you should ask yourself, what am I getting at here? When I read this at the beginning, at first I thought, this is quite complicated. To explain something simple, it is really complicated because we already know how linear regression works. Why do we need to understand this? But it would allow you to understand the concept, the two precious concepts in machine learning. One is MLE, another is MAP. Right? These two concepts are very crucial in understanding different types of model. Right? Let's see here. Right? Instead of looking at a way to minimize parameters in linear regression as least square process, we now explain it as the likelihood to get to correct value. Okay, and now when we decompose this log, we get the log of 2 pi because it's a square root of 2 pi. It's actually 1 over, right? So we can reverse it. This is just constant, doesn't matter. Let's think about it in other time. It's just a constant. And the log of 1 over sigma would be minus of log sigma. And this, so this is just putting it up and putting 1 over 2 down here. And the last part is the deviation of y and y hat. Okay, now we can distribute m into each terms. The first part would be the summation of constant would be m over 2 and log 2 pi. This is again m and log sigma. And the last part would be the summation of m of y minus y hat of prediction and square and 2 sigma square. So what does it mean? It means that the MLE criterion lead to sum of the square errors. That means sum of the square error is the MLE criterion after all, after all that we have been doing, right, we end up with, yeah, sum of square is MLE, right? So diff MLE equal diff of sum of square. So I will just diff sum of square all the time. I don't want to work with this conditional log pop. But yeah, that's the way to prove that. So it means that the MLE for linear regression is actually the sum of squares. So it means that when you derive, when you take derivative of the sum of square errors, you actually find the best solution for the maximum likelihood of problems. Okay, now let's take a look at the properties of the MLE, of the maximum likelihood estimators. The true distribution would have to be would have to lie within a model family. What does it mean? It means that the distribution must be contained, right? Must be contained in the distribution that the model can explain. Right? Basically, the model has to have parameters to capture the data, right, from this interpretation, right? And the true distribution of data, right, must corresponding to one parameters, must correspond to one parameters. Otherwise, MLE would be able to just determine the best value for data generation. This is the same way as explaining that when you have multiple equations more than the unknown, and then you need to have like best estimate out. Right? But a little bit complicated way. Now let's take a look at the last one. This last one is a lot more complicated than the earlier one. Earlier one is like, alright, it's still, you might still be able to grasp that. I have a difficult time, so for MLE is okay, it's easy to understand. You just take a look at it in the perspective of, right, error and so on. MAP, on the other hand, this is the maximum posteriori, or the MAP. This actually, surprisingly, has been used in a lot of machine learning model in order to derive the model parameters. Right? MAP use Bayes rules to derive, to work with, right? What does it work? How does it work? So Bayes rule decompose the components of the probability into multiple parts, right? We have the probability of W given D, right? Or you can think of the weight given data, right? Equal probability of data, probability of D, and the likelihood is probability of data given W, and the prior is probability of W. So think of this as probability of having disease given certain data would come from likelihood that it's probability of getting disease with that data, and then probability of the disease divided by probability of the data occurring. Okay, so this is MAP using the Bayes rules. So in MAP, there is the basic assumptions of MAP. The basic assumption is that there is a prior. There's prior happens. So when there is a prior, in order to find the best model parameters, you need to also consider prior as well, right? Not just likelihood, but also prior. And this one is not important, right? But not just likelihood, but you need to also consider prior. Once you consider both of them together, you get the posterior probability. And the idea here is to find the maximum of the posterior probability. Okay? This is a quite classic notion in machine learning. Like in the year 2000, I read a paper on hidden Markov model. It actually explained everything in the MAP style in order to estimate the model parameters from the model. A lot of classical mathematical model used in machine learning nowadays actually use the MAP as well. After like incorporate prior and likelihood together, they can come up with the way to find parameters there. So the basic assumptions of the model is that it must have prior. Right? It must have prior. Let's see. Let's incorporate that into our model. Right? That is, we have like multivariate linear regression, and we have this assumption that the means of parameters should be 0. Right? The means of parameter combining should be 0, and the constant variance as alpha. We kind of imposing this into the model, and that would make the probability of the PW, the prior values. This would be directly proportional to these terms. That is the weight, right? Minus the weight has to distribute in the normal distribution manner again, right? Say here it should be like this one. All right, and we assume that okay, this is the weight. Expectation value of the weight should be 0. That's why we substitute 0 here into the distribution, into the parameter distribution. You may wonder why the normal distribution has to write this way, because actually if you take a look at the normal distribution, you will notice that this term, the value minus mean, should be square, right? Should be square. But for the square of the multivariate, right, because we have multiple weight, it cannot be square. It has to be matrix multiplication. It has to be explained as the matrix multiplication. And so this would be the decomposition of the matrix in the SVD form, singular form. This is like W minus mu, and this is W minus mu as well. This is transpose and the eigenvalue. So this, well, think about this as just W minus mu square, right? But write it in a little bit more complicated, a little bit more correct way mathematically, because they are both vector. You cannot write them as this, right? So I write it is written at this way. So now if the mu becomes 0, we have W, and this is also W, and the eigenvector. So see, finally, it's like square again, right? So it's just like you just put 0 here. You just have W square. W square doesn't exist in matrix terms, so it's like W transpose times W. Right? Mathematician often make things a little bit more complicated. Exponential, right? Here, inverse, that makes alpha coming up. This alpha is the variance of the parameters. That means once you impose that value, right, high value of alpha, then, well, you can see that this is exponential of the weight. Now, if we incorporate this into the likelihood, right, the likelihood of the linear regression. This is the linear regression, the same one that we talked about in the past few slides. Right. So here we have the basic assumption of this is the distribution exponential of y and minus the model square, this one. And you can see that this is directly proportional to this part, right? The first part can be disregarded. That means when we convert this into the probability of d given w, right? This would be the multiplication of multiple points of data, right? Because we have multiple points of data, right? Multiplying the probability together to get the likelihood of having correct w. And for the MAP, this is log of PW given D, which is log of, this is the log of MAP, taking log in order to just separate them into the combination term. We have log of PW given D, this is already defined, log of prior, and log of data. Right, now we already have all the terms. We already have log of data. Now we already have log of prior, right? We did. Right? We have the prior. The log of prior is actually this term, the weight square. Right. So disregarding this one doesn't matter. Doesn't matter on how the data happen. So in the end, W would be the argument max of the log of posterior probability, and that is actually the combination between the log of the likelihood, right? The log of the likelihood and the log of prior. And what are they? One is the what is this? We know that this is the mean square error, because when you take log of this term, you get only this term. And the log of prior is actually weight square, sum together. That means, yeah, it's the same thing that you are working on right now, right? Your assignment is actually trying to do the MAP optimization of the logistic regression. Yeah. So this is the argument max of the first term and the second term. The first term is the likelihood. The second term is the weight. In combination, you can see that the MAP criterion roles in machine learning is to highlight the need to have regularization terms. And this regularization term comes from the prior assumptions of the model parameters. And usually this would be the assumptions that the model parameters need to be small. And the model parameter needs to be small. For this particular example, we set the expected value of the mean of parameters to be small, to be 0, to approach 0. That's why we have this to minimize. Okay, so this is also another interpretation of regularization. Regularization is the byproduct, or actually it's the direct product of the MAP derivation of the machine learning problems. Alright, so that's it for today. There's no assignment further because you already have your own assignment, and what we have covered today is actually part of your assignment. And then you can see that finally, at the end here, we are still talking about the regularization in the optimization process. And that is, the MLE would give you the data constraint. MAP will give you both the data constraint and the parameters constraint, or the usage of parameters, the constraint that relate with that. Combining them, you have a nice framework in machine learning to estimate the model parameters from the data. Okay? Yeah, and that's it. It would be a little bit overwhelming, especially particularly in the last 10 slides for sure. I would suggest that you try to review the model derivation step by step, and if you want detail, again, read the book. It should be in the basic machine learning, although, well, it will be more, the book would explain things a lot more than what I explained in the class, but I think some of the notions are a little bit hard to understand, tell you the truth. Like if we jump to the MLE 128, right, so what I try to do here is to summarize them so that it would be easier to understand. But in the case that you want more detail, I would suggest that reading the book in the Goodfellow books here. And it has more example. For example, it has example on the decision tree and explanation on decision tree and support vector machine as well for the task. Okay. But in any case, these are the points that I want to convey for this lecture. That is, the two main criteria in machine learning plays important roles in all of the machine learning fields, including deep learning. You can see that in order to get best fit with the data, MLE criterion would express that you need to find the best way that the model distribution should be able to express the data distribution. That's the MLE, maximum likelihood. MAP, on the other hand, include prior distribution into consideration. That is, you need to consider the probability after considering prior and likelihood together. That's why it has the name posteriori, the posterior distribution. And that makes prior becomes regularization constraint in the usual machine learning definition, right? So this is the mathematical foundation of MLE and MAP. Actual implementation would be different based on different type of regularization. For example, in deep learning, you can find regularization in terms of dropping the value directly. So it can be, but the aim would be the same. That is that you're trying to minimize the number of parameters out of the overall things, right? And when you read your papers, trying to think about this framework, and then you will see that probably I would say most of the algorithm proposed need to contain these two constraints or multiple constraints that carrying the information like this, that it contains something like the data, right? The model and the data fitness as one part, and something like the smoothness, regularization, or the still smoothness of the data itself or of the parameters as another constraint, and that would relate to the prior distribution here. So when you think about your own algorithm, maybe you should include this in the optimization, and that would you can see that would consider not just the fitness alone, which can result in overfitting, but also the prior distribution, right, to make it better in terms of the optimizing of parameters. The book name, right, is in the syllabus. You can take a look at the syllabus. Is Deep Learning by Ian Goodfellow. The book is mathematical oriented, right? If you want an more of introductory in deep learning, I would suggest the one, I don't remember, is the deep learning in Python or something. I don't remember the mascot in front. Let's see. Well, tutorial by Andrew is okay as well. Yeah, the one in. Actually, you can just take a look at this link. This is a good reference. I have them all. Right. We use the Goodfellow for reference in the deep learning course, but for the undergrad who have already learned coding in AI, I suppose I use the deep learning with Python by Schobert, right? And it's a good one as well. The one that about scikit-learn and TensorFlow is also okay. Okay, I should share the screen. Right. So these are the good books. I think we are using this one. For implementation, I would suggest this deep learning with Python. It is okay. It is okay. It has a little bit limited explanation in mathematics, but it has quite detailed explanation in coding. So I would suggest using it, studying it together with Goodfellow book, right? And it should be fine. All right. So that's it for today's. Keep working, right? You still have assignment to submit. If you have questions, you can ask. Your friend already asked, and I made a mistake in the notation. I forgot the square there. Right? But yeah, well. Can we have an ungraded review test before the exam? The exam format, right? The exam would be written explanatory. Right? I think last year I gave the exam. I don't remember, but I won't show you. Let's see. Well, the exam are more of the explanation. It will relate to the thing that you learn in the lectures, and it will relate to the thing into your work in your assignments. All of them would be explanatory. It means that you need to work on that, just quiz or something that has similar patterns to the exam. All right. Let's see. Yeah, let's say I will consider that, right? Because I think that that's a good idea as well. But yeah, I will try to do it to have maybe few quiz on the questions that we have already learned. Well, the quiz would not be because we learn in this format, so the quiz would be also offline. That is, I will post it into the class marker, and then you have to just do it before the deadline. The deadline would be like 1 week, like this as well. So it would be like I would not like quiz online here. It's like you have to quiz before the class sometime. But maybe I will announce it on the group so that you can take a look at the format and maybe gain some score earlier to that. All right, thank you. Yeah, I'll do that. That's a good idea. Okay, so let's call it a night. Have a good night, everyone. See you next time.